Welcome back to the course. In this lecture, we'll take you to the lab. For the laboratory demonstration, the lab is 4I lab in IIT Kanpur. This is an advanced machining, advanced manufacturing lab at IIT Kanpur, which is an elite facility that we have here. And like we have seen different rapid prototyping techniques. In this lab demonstration, we'll just discuss 3D printing. 3D printing using a specific machine that is there in the lab. The name of the machine is TechB V30, and our laboratory demonstration, the instructor is there who has made this video, and we were in the lab, we developed this video, and I am trying to put my voice to demonstrate it properly. So let us start this and go to the lab.
So right now we are in 4I lab. It is the facility in IIT Kanpur. 4I. 4 I's are innovation, incubation, implementation and integration. In this laboratory we have multiple machines which are non-conventional and advanced machines. We do research and also consultancy is being carried out here. So at this point of time we would like to discuss about this machine TechB V30. We will start with the demonstration of the software that is used for rapid prototyping here. Then we will set up the machine, we will make the whole setup. Then we will see how rapid prototyping various features, various parameters are taken into account while manufacturing. This is additive manufacturing, as I mentioned earlier.
This is a 3D printer. TechB is one of the companies in India that is manufacturing the 3D printers. So this uses FDM technology. FDM, as we have discussed, FDM is fuse deposition machining method. There are two major kinds of machines in the machine sections, as we know now, FDM and SLA. FDM is fuse deposition machining and SLA is stereolithography operators. Okay, I would like to put some light. In FDM, there is a big variety of colors that those are available, like we can have red, yellow and white are the major colors. Also, there are certain companies who are manufacturing the colors based upon demand. But in SLA, the color variety is not possible. There are certain differences in FDM and SLA. This is only FDM machine. This has two spools, two nozzles in which we can use two colors, and the multicolor or the bicolor products can be made. Okay, about FDM and SLA. FDM machine produce products with the precision, but the precision level in SLA is higher. The higher resolution objects are more possible to produce in SLA because resin is there. The resolution is primarily determined by the optical spot size either of the laser or the projector, and that is really small in SLA. In FDM, it is the printer. The printer resolution is a factor of the nozzle size and the precision of the extruder movements. That extruder we will discuss in this demonstration as well. The precision and smoothness of the printed models is also influenced by the other factors such as bonding force between the layers, is it lower or is it adequate, then the weight of the upper layers that squeeze upon the lower layers, the number of printing problems like warping, misalignment, these printing defects might be there, shrinking, shifting of layers, all those things could be there. And there is a difference in post-processing as well. In general, FDM requires no or very little post-processing because the products are generally produced to the final shape. Only the thing is that the support that is provided, the support material or the brim or raft that we will discuss has to be removed. In SLA, post-processing level is quite higher because it is made of resin, and all the extra material that is there has to be removed and it has to be taken out from the box where it is made. So there is a big difference. So where we are more focused on FDM, fuse deposition method. So this machine, that is FDM machine, deposition method of fuse deposition machining, this machine can use two kinds of filaments, or there are multiple filaments like ABS, then PLA. It can use ABS, PLA, and ABS is acrylonitrile, butadiene styrene, as we know, and it is oil based plastic. It is strong, sturdy material that is widely used these days, like Lego building blocks, Lego toys are made of this ABS, to quote an example. And PLA is one of another materials. It is polylactic acid. It is made of organic material specifically from the cornstarch or sugar cane. It makes the material both easier and safer to use while giving it a smoother and shinier appearance. So it has more aesthetically appealing products which are made out of it. Now this PLA thermoplastic is also more pleasant on nose, like it smells lesser, like as the sugar-based material smells slightly sweet when heated opposed to the harsh materials associated with ABS. When we heat ABS, the smell is quite annoying. In PLA, this is not the case. So this means that the printing using these parts, it's more friendly for the operator. And also PLA seems like a better overall choice because it features far low melting points as well. The melting point of PLA is quite lower than ABS. So I wouldn't move into that track now. So let us discuss about this machine. This machine is basically using FDM technology. The raw material moves from the tube and comes up to the head, that is the nozzle around which heaters are there. And when we switch on the machine, the heating systems gets on. When we switch off the machine, the heating system gets on. There are two nozzles here, nozzle A and nozzle B, you can see. So the temperature, when we switch on the machine, the temperature rises and it goes up to 200 to 230 degrees centigrade. At this temperature, the raw material kept in the form of wire comes out near the nozzle, it comes out through the nozzle. So it is coming through this tube. We will show this demonstration. Now this portion is known as head, where the nozzles are attached. So the material is fused and comes out from these nozzles. These are two nozzles here, nozzle A and nozzle B. Why two nozzles are there? We'll just explain. One nozzle is for the base material, another is for support. So this is a very fine orifice of the nozzle. That the orifice dia of the nozzle is 0.4 mm. 0.4 mm. When all this bed area maintain the soaking temperature of the bed of 50 to 65 degree, 50 to 65 degree temperature is maintained here. The temperature, it heat up a little bit. So as it temperature is, it is actually the preparation of the table. It is heated to some specific temperature so that the material that is deposited here, the temperature of the material is about 200 degrees. This temperature is kept about 50 degrees so that it can stick easily, so that it sets easily here. So this will have to deposit one layer upon another during fabrication or manufacturing. Whatever we want to fabricate here in FDM technology, the machine size is, this machine size is 1 feet by 1 feet by 1 feet. So in XYZ directions, the envelope is 1 cubic feet, I can say. 1 cubic feet envelope is there. So it is just plug and play machine once we have a little practice on this. Along with the hardware, we have a software here that also gets on when we switch on the machine. This is the software. When we switch on it comes Tech B. So Tech B is the machines. The software is switching on. This Tech B software is getting on. You can see slicer 1 and slicer 2. The two slicers are there. Okay. So there are CPU and controllers which are here at the bottom surface of the machine. CPU and controllers for this software is here. So the two nozzles, one for model and one for support, one for model and one for support, two nozzles are there. So if any profile or any geometry where we find this taper is more than 45 degree, we need to provide support like I discussed. Then the two nozzles will automatically activate and that will provide us support to produce the final product, final model that we need to obtain. So this all feedback is given to the head with the help of software that will be described later on. So precautions while we use this machine are certain precautions. When we try to switch on this machine, the nozzle is quite hot, so we cannot touch the nozzle with bare hands. Also we need to place this machine, it is general precaution, we need to place this machine in room temperature. Air conditioners are not recommended because humidity or moisture would hinder the quality of the product. And we also need to avoid mishandling or prevent the machine from any rough handling, and the nozzle cleaning is very important. Nozzle cleaning has to be done before machining, but hot nozzle shouldn't be cleaned with hand. That is very important here. So there are certain sharp edges in the machine as well, sharp edges like in the nozzle head, or certainly sharp edges are there. We need to be careful that we do not touch these sharp edges, and be careful in this is the safety precautions when we start the machine. Next, with this machine we can manufacture parts with sharp corners, any areas, any radius, and the profiles with pocket, the profiles which are empty inside or is hollow. And one more feature of this machine is that we can print two different color models from these two nozzles, nozzle A and nozzle B. If the two different colors can be obtained, like yellow and red, different colors can be obtained and those can be produced as well. So on this computer screen we have a software called Repeater. So we have slicer 1 and slicer 2 here. So if the machine is with two heads, with both hands we individually work. In this machine there is a single head. If the two heads are there, the machine, though both heads can work independently. So, you know, there is single head here, single head. On the single head here, two nozzles are attached. So that is why only slicer 1 is visible here. So the software is starting on. Repeater software is starting on. Repeater host is a specific name of the software. 6.2 is the version. Then we need to connect the software to hardware. Now both are interfaced with each other. When we start machining, that is, try to fabricate anything on 3D printing, we have to take care of number of things like cleaning of bed, cleaning of head nozzles, and proper cooling as well. For cooling, we have to check that there are two fans. Two fans are just above the head, that should be running. So whenever we start the fabrication of this machine, we have to take care of few things like proper cleaning, flatness of the bed, and we can adjust the level of the bed with 4 screws. You can see this screw 1, 2, 3 and 4. 4 screws are there. So these 4 screws are loaded here using spring mechanism. So when we fabricate a model of big size, the height will increase, height increases, and sometimes it will vibrate due to the height, and gapping will vary. So that is why the spring loaded mechanism would help to adjust the movement in the nozzle. So you can see there is a spring mechanism here. So that helps to adjust the movement. So in this way, we'll make the leveling of the bed. Also, whenever we go for calibration, so we use these screws to loosen and tighten and to make sure that the bed is flat. It is secure with its adjacent surface as well. So in this software, we can deposit layer thickness in slicing from 0.1, 0.15 and 0.2, the 3 levels here. Whenever we change this parameter of deposition of layer height wise, then we need to maintain the gap as well. So let me say I have fixed 0.15 from the top of the bed to the tip of the nozzle. So we need to set this gap and lock the limit switch. The limit switch is on this side. Limit switch is on this side. So we can lock the limit of the bed using this lathe. So bed can move up to a specific limit only. So bed would go up or down as per the locking that we make here. Also, whenever we start depositing fabrication of raw material, we have to take care of a few things like what are we feeding here. Because the raw material is in the form of a spool, it is an open spool kept at the back of the machine. It is there, spool will just show you. We need to take care of it because when we attach this material in the boxes, we have to use silica and calcium, and this makes it moisture free. If our raw material, that is, as I mentioned, ABS or PLA, if it is moisturized, then it obstructs the proper deposition of the job here. Whenever we input the data to the machine for fabrication. After switching on the machine, we have to take care of few things on the display here. You can see this display because the hardware that is connected to the software and displayed to this screen. On the screen we have program. We start feeding the data to the hardware. We have to take care of number of things after switching on the machine. After switching, the machine itself gets connected to its software. Whenever we start, we have to go to the option number 1, that is object placement, which means that what we need to print, we'll place it here first, the placement of the object here. So when we click on when we click here, a few things will be highlighted, few icons are highlighted, like this add object, this plus sign is add object. So what we want to add, we click add object here, and when we click it, it opens the drive or the location in the computer, like the COD drive where the object is kept. So wherever we have kept the CAD model for fabrication, whatever we want to fabricate, we can just go and click there, or we can even generate some model. So this model known as rubber Bhargava Viru, this model is there. So we'll click here. So yes, when we click here, this job is there here on the envelope. What is envelope? Envelope is this where we are going to manufacture this thing. So this is 1 cubic feet, that is 1 feet by 1 feet by 1 feet. The envelope size is this one. Okay. So this area is 1 feet by 1 feet. I can say that on the area of 1 feet by 1 feet or 1 square feet, this object would be manufactured. Okay. So actually this is our base plate where it is manufactured. So this is our envelope that is being displayed in the software. The approximate size of this model is 4 inch by 1 inch by 2 inch. So whenever we start fabricating, we need to see the program. We have to program it. Either a program would be generated by machines, by the software itself, or we have to manually program using G codes that we will discuss. So this job of this height of the entire job will cut in number of slices here, number of slices. Okay, how many layers would be there, that the machine would just decide. So we have to program in terms of slicing, and the machine will deposit one slice in one stroke, and this will be deposited layer by layer and finally becomes a complete job. Here in object placement, there are other icons like copy object. Copies, like we can make 1 or 2 or 3 copies, like we are making 2 copies, the 3 copies are made of this object. So a single CAD model can be printed in multiple models using this command with just copy. Okay, this is product design, CAD, computer aided design. Yeah, this is auto positioning. Auto positioning, what is auto positioning? So when we need to print at the center, auto positioning will bring the object at exact center in the envelope. So we need not to drag it, like we were dragging before. We need not to drag it. Okay. Next one is center object. Auto positioning. Auto positioning, it will position the object so as the least material is used. Center object is similar to auto positioning. In auto positioning, what happens? This is auto positioning. In auto positioning, what happens? It places the object so as the minimum material is used, so as the material has to travel the minimum path. And in auto centering, object will be placed at the center of the envelope, exactly at the center. Like we were dragging, like we might offset the object while dragging manually, but this will be placed exactly at the center. Now, yeah, this is scale object. Now here scaling means changing the size of the object, making it oversize, undersize, or upscale and downscale are better words. You can say X is made twice. Okay, X direction is made twice. Now Y is made again twice, thrice. We are scaling the object. So upscaling this one. You can see it is made 0.5. So this is scaling of the object. Sometimes the CAD model we draw is big and we just need to produce a prototype or just a field model out of that. Then we can just downscale it and produce. So this is a direct provision for that. This is a direct feature in the software for this one. So next icon here is rotate object. Sometimes like we have discussed that the placement of the object or the alignment of the object is very important in deciding the support material that is used, or the amount of support material that is used. So to properly align the job, like in X direction we have aligned it to 90 degrees. So this is rotation. So we can make the job in this position as well, like if we see that how much material would be used, lesser material will be used. So support material that would be consumed would be lesser, can be reduced by deciding or by selecting the specific alignment here. So sometimes we have the pure flat surface. If there is flat surface, it is the perfect thing. The flat surface, if you will deposit properly on the flat surface, it is exactly perfect. But you can see that we have an angle here. In this we have a little angle here, like we need to have some support here. So for that we need to see what should be the proper alignment so as this support is minimum. So we rotate and try to keep the CAD. CAD is this model, computer aided design model. We have, I'll keep on using the word CAD for this model. This CAD is kept in proper alignment so as to minimize material use. Look, y is kept 0, x 90, z 90. So if y is kept again 90, so the height increases. What is the drawback when we increase height? When we increase height, because it is manufacturing layer by layer, this is very important to note. If we increase the height, the total time would increase. So the height has to be optimized, it has to be minimum. You know, these many number of layers are to be deposited, so the total time would increase. So total time means total economy, total cost of the product will also increase, because in product cost function the machining time is one of its factor. So this is not a very good position to manufacture here. So we can opt to select in flat position and we orient the job in proper place and position. So next is view cross section. This icon is view cross section. Sometimes we need to see what is in the inside portion of this job. So when we need to see the inside of the job, for example, we have called this CAD model from the customer. The customer has just made this model, brought this model for us. So we are not aware that what is the profile inside. Are there any holes, some pockets, some countersink holes? So if the customer is not able to describe it properly, the manufacturer or the operator has to be very careful. It is a duty of the operator to be conversant with what he is going to manufacture. Then the manufacturer has to take care of everything. We use this icon to check it in the section view. You can see. So blue is the upper surface, blue color is the upper surface, and green color is inside. What is inside? So this is the color difference, color coding is here. So blue is the upper surface. Inside it is a solid model, it isn't hollow, it is not hollow from inside. This is the inside model. So we can just in view cross section tab we have this bar position. Okay, we are checking the position from here. So major purpose of this is to identify whether the model is solid or hollow. If it is hollow, then we have to be careful about the thickness. What has to be thickness of the surface? The thickness of the shell has to be according to the requirement. It has to be according to rigidity, whatever requirements we need. So this is again is inclination. Inclination at some angle also. You can see the angle is changing. This is 0 angle. This angle is about 90 degree here. So this is azimuth. So we can rotate it from the bottom here. We can see another viewpoint from this. So in this way, using these three tabs, we can see each detail. For instance, there are multiple features, deep features or the intricate features in this job. We can see that what is there inside the job, provided the CAD model has all those features. Now this is the actual part of now. Now the last one is very common thing, mirror object. This is mirror object. This is we can change from left to right or right to left. So now what we identified that the placing of the CAD has to be proper. Only then we can go to less level, it is slicing. Okay. So next tab is slicing. So this is, I can say, the most important tab because we are going to discuss this slicing here. So slicing with Cura engine. So Cura engine is the software that is used for slicing here. So slicing, the time used in V30, this machine V30 is Cura engine. So it cares the quality of the product that we need to manufacture. It will discuss everything like thickness, wall thickness, quality, support, then volume, time. So the word engine means it is the heart. Word Cura engine, I just can say it is the heart or lifeline of the software. So this whatever we need to fabricate would be majorly decided by this portion only. Now we have manager here. Manager tab, when we click the manager tab, this opens, this window pops up. The manager is for the advanced version. This is for instance, this manager is here. This is for the advanced, for instance, some manufacturer is there, some big manufacturer is there, and he need to calibrate the machine, he need to go to the advanced settings, then he can use this manager. We would not use this. Next one is configuration. When we click the configuration, what we can see, we have this Cura engine settings here. So there are two tabs here, filament, very important here, and print. What is filament? Filament is the raw material that we are using for printing, like I mentioned, ABS or PLA, that is there in the filament form. This is the raw material, this is filament. So this is white color, ABS filament, this is rolled on a spool. So it can be white, it can be red, you can say red and white. So white is the most common color that is used in FDM technologies nowadays. So white and yellow, actually white and yellow are the most common colors that are used in FDM technologies. So this is 3D Cura, 3D view. In Cura in the sense giving a 3D view, temperature curve and Cura. Temperature curve, we can just see when we actually do machining. So nozzle, at the nozzle heaters are there, heater is supposed to heat. So to fuse the raw material, heaters are heated. So the orifice, from the orifice the material would come and this temperature would be shown in the window. So in the Cura we have these settings. So we can talk about print or filament here. This is print, this is filament. The very first thing is speed and quality. Speed and quality are two interrelated terms. I can say the opposite terms in this specific machine, because if the speed is higher, the quality would be a little lower, and if the quality has to be good, the speed cannot be very high. So speed and quality, like it has to be optimized. So that is why this term speed and quality is there. Like while deciding these different parameters in speed and quality, print, travel, I'll just discuss this. Also the automatic setting is also is there in the software as well. So speed and quality are interrelated. So we don't want to waste the material, we don't want to lose time to because that would increase the cost. If we lose the material, that will also induce some cost. Next is structure. In structures we have shell thickness, top bottom thickness, infill overlap, infill pattern. So we will discuss this one by one. So let us come to speed and quality first. Speed and quality. So we have print, travel, first layer, outer parameter, inner parameter, infill, skin infill. What are these? Let us try to discuss this one by one. So what we have, we can have the limits here for the any of these parameters, any of these manufacturing parameters I can say. Okay, print the slowest speed and the fastest speed. So at slow it is kept 40. So our purpose is that the material that we drop here should stick with the base plate with this. If it doesn't stick, then there is a complete wastage of the material, and even the part might not build properly. So the travel speed of the nozzle has to be decided. So it is kept slow and fast. It is same, that is the fixed speed is 40 millimeters per second. For printing it is 40 and 40. For travel means when it is not printing, when it is not productive, it is moving just ideally from one place to another, the speed is high, it is 150 and 150. 150 means both 150 slow and 150 fast means the speed is fixed to 150 millimeters per second. So you can see the first layer is kept 40 and 40 and outer perimeter is 20 and 20. So this is a important thing to discuss here. So if the part is hollow from inside, then we have to be very careful about the outer shell. So it is mandatory, or it is I can say compulsory, that the outer surface becomes really smooth and shiny, and up to the size, up to mark, and the dimension of the profile should be accurate. So inside filling can go fast, but outside surface, that is the periphery of the jobs, needs to be of high quality, so good finish. We always take care of the outer parameter speed, that is kept lower, that is 20 and 20. Okay, 20 millimeters per second, 20 millimeters per second for slow and fast both. For filling it is 40 and 40 again, so that is not very significant. So in the same way, inner parameter is 30 and 30, inner parameter is 30 and 30, and the infill, if your job, your part is solid, if the part is solid, the infill, the inner part, whatever they filled in is called infill, that is 40 and 40. Okay. Another parameter here is skin infill. Skin infill is kept 30 and 40 millimeters per second. So this is quality and speed. This is speed and this is quality. Speed is also related to quality in one way. It has mentioned another term, quality, here in this tab. So what is the quality? That is the quality of the layers that we are going to deposit here. Point 1 is very thin, is very fine, so it is highest quality. 0.15 is a little higher, and the lowest quality is 0.2. So if the layer thickness is 0.1, the job would come very smooth and shiny. If it is 0.2, it would be the worst among these, and 0.15 is in between. So 0.2 mm means that it consumes less amount of time, but the quality goes down. So in this way, sometimes you find that our dimension here or our profile shape is important. So quality factor is not very important, that only the profile shape is there, then we can go for rapid printing, that is 0.2 mm can be. Sometimes we feel that the size and dimension as well as quality that we need to keep has to be higher, so we can keep 0.1 mm layer thickness. After setting all, we go for the next thing, that is called as structure. Okay. In structure, we have shell thickness, it is set as 0.12, top and bottom is 1.6 mm, shell thickness is 1.2 mm, top bottom thickness is 1.6 mm. So infill overlap is 15%. So what is basically infill overlap? When one bead is deposited over the other bead, it will overlap. So it can't, if it doesn't overlap, it can't stick with the first layer. So the first layer will stick, with the second layer. For instance, this layer thickness is 0.1, the second layer thickness is again 0.1. So there will be some overlap. So this overlap, how much overlap we can keep here? So what will happen? It will displace the nozzle. If this overlap is not here, this is 0.1 and this is 0.1, the nozzle will touch this one and it might displace the nozzle, the part might distort. So some overlap should be there, so as there has to be some gap here for the nozzle to work in. Okay, some gap at this surface has to be there. So for that, this overlap limit is given. So this overlap limit can be 15% or 20%. So this is kind of an overlap. The second layer wouldn't be exactly on the top of the first layer, it will be a little overlap. In this case, you can just see like the fingers, we are just trying to try and demonstrate that 50% of 50% of overlap can be seen here, but it is 15% of exact overlap would be there if we put this input in the machine. So this bead is deposited in this way. So sticking the layer would not be proper if this overlap is not there, and the proper overlap, that the fill amount of 15%, then there is an overhang angle as well here. Okay. So overhang angle is 60° here. So overhang angle here is for the machinery, for this machinery. If we are going to deposit, better say deposit or print or manufacture any job, if it is solid, there is no issue at all. If it is a conical shape, an angle is up to 60°. Well, 60° means if the angle is 60° like this, if it is above 60°, nothing would happen, it just deposit slice by slice. But if angle is more than 60° here, it has to have supports here, like it has to have supports here to support the material. So this overhang angle that we can decide, okay, that we can decide overhang angle has to be fixed, that is fixed at 60° here. So this overhang angle is 60°, and next what we have here, so we need to see that is there anything overhang in the CAD model. In the CAD model, if anything overhang is there, then we need to put this angle. So if anything is overhung, then we need to provide this support, and only then we can proceed further. So then overhang angle has to be decided. Next is extrusion. So this is extrusion of the filament from the spool to the nozzle. So this is a retraction speed. Retraction speed is 40 millimeter per second. Retraction distance is 4.5 mm. There is basically a roller at the back of the machine that is responsible for bringing the filament to the nozzle. So there are two rollers and the filament passes through them. The filament moves through them to a tube to go to the head. So this retraction speed or feeding of the raw material is 40 millimeters per second. So as per our speed of printing, whatever the speed of printing is there, that speed would be kept here, okay, in the extrusion. Now retraction distance is 4.5 mm, and a number of considerations are there, but these are not very important because when we are going to servicing, we are going to service or overhaul the machine, these things are set by the G code, because when we go for overhauling or service of the machines, these things are set by the manufacturer or the provider themselves. Next one is G code. So we are talking about slicing here, okay, this slicing with Cura engine. In the slicer, when first we had object placement, when we have slicer, second tab here. In slicer, there are multiple options here. Now this is G code. So slicing is nothing but depositing the layers, but how to control the movement of the nozzle in the X, Y or Z direction, that has to be taken care by a program. And this programming system is known as G code programming system. If you know CNC programming, G codes and N codes might be conversant. And this programming system is known as G code, and G code and M codes are both there. These are mostly used for CNC programming like milling, turning and other machinings. The same code is used here in 3D printing for the movement of the head over the bed for depositing the material. We will meet in the next lecture. We will discuss further about the course. Thank you.